Mass is usually described as something objects carry, but modern physics shows a quieter and more unsettling picture. What we call mass depends on a field that fills all of space, even where there are no particles at all. The Higgs field is present between atoms, between stars, and across the expanding universe, holding a constant background value that never switches off. When elementary particles move through this field, some interact strongly and slow down, while others pass through without resistance. That difference alone determines whether matter can clump, whether atoms can exist, and whether stars can burn steadily for billions of years instead of flashing out in an instant. This is why the Higgs field matters to cosmology as much as it does to particle physics. It decides whether the universe can ever form long-lived structures or whether it would remain a fast, radiation-dominated plasma. And this leads to a question. Why does empty space decide whether anything can ever be heavy? If the Higgs field truly exists everywhere, then the most disturbing conclusion is not about particles at all, but about space itself. Mass is not something matter owns first. It is something the vacuum permits. For most of human history, weight and heaviness felt intuitive. Stones fall, mountains stay put. Stars burn slowly instead of exploding instantly. It feels natural to assume that mass belongs to objects in the same way color belongs to paint. But modern cosmology forces a reversal of that intuition. In the framework of quantum field theory, the same framework confirmed by particle accelerators and cosmic observations, particles are not fundamental objects moving through empty space. They are excitations of fields. And among those fields, the Higgs field is unusual. In one deeply consequential way, it does not vanish in empty space. It has a constant, non-zero background value everywhere the universe exists. This means that what we casually call empty space is not empty at all. It is filled with a physical field that never switches off, not between atoms, not between galaxies, not even in the deepest cosmic voids mapped by modern surveys. The Higgs field is present in regions where the density of matter approaches zero, and its presence is measurable through its effects on particle behavior. This is not philosophical language. It is operational physics. When particles propagate through space, their equations of motion include terms that depend directly on the Higgs field's background value. Remove that background, and the equations change in a way that eliminates mass altogether. To see why this matters cosmologically, it helps to recall what the universe looked like in its earliest measurable moments. Observations of the cosmic microwave background by missions such as WMAP and Planck show a universe that began in an extremely hot, dense, radiation-dominated state. In that environment, energy moved at nearly the speed of light, interactions were frequent, and nothing resembling atoms, nuclei, or long-lived structures could exist. The universe was fast. Everything behaved like radiation. The crucial transition from that fast universe to a slow one depended on something subtle, the emergence of mass as a meaningful property. Without mass, particles cannot linger. They cannot orbit. They cannot bind into stable configurations. A universe with only massless particles is a universe without chemistry, without stars, without galaxies, not because of any aesthetic preference, but because the equations governing motion and interaction never allow energy to settle. This is where the Higgs field quietly enters the story. In the standard model of particle physics, elementary particles acquire mass through their interaction with the Higgs field's constant background value. Technically, this background is described as a vacuum expectation value, a measurable non-zero quantity that characterizes the lowest energy state of the field. When particles couple to this field, their motion through space is altered in a precise, calculable way. Their energy-momentum relationship changes. They behave as if they resist acceleration. That resistance is what we measure as mass. Importantly, this is not an analogy. It is not that particles are slowed down in a metaphorical sense. The presence of the Higgs field modifies the terms in the Lagrangian that describe particle dynamics. Those modified terms survive, even when no particles are present nearby. The vacuum itself carries structure. This leads to a radical but unavoidable conclusion: whether the universe can ever become heavy enough to form structure depends on the vacuum state of a single quantum field. If the Higgs field's background value was zero, then electrons, quarks, and the carriers of the weak force would all behave as massless particles. Nuclear reactions would proceed differently. Weak interactions would remain long-ranged. Energy would flow too efficiently. The universe would expand, cool, and remain fundamentally unstructured. Historical context sharpens this point. In the 1960s, when physicists were struggling to unify electromagnetism and the weak nuclear force, they encountered a severe problem. The mathematical structure of gauge theories demanded massless force carriers. Yet experiments had already shown that the weak force is mediated by very heavy particles, the W and Z bosons. Giving these particles mass by hand broke the consistency of the theory. The equations simply stopped working. The solution, proposed independently by several groups, including Peter Higgs, François Englert, and Robert Brute, was to allow the vacuum itself to break the symmetry of the theory. Instead of inserting mass explicitly, the vacuum would choose a specific configuration. In doing so, it would allow some particles to behave as if they had mass, while preserving the mathematical structure of the theory. This mechanism did not merely solve a technical problem. It redefined what empty space meant. Decades later, in 2012, the discovery of the Higgs boson at CERN provided direct experimental confirmation that this field is real. The ATLAS and CMS experiments observed a new particle with properties consistent with a quantum excitation of the Higgs field, with a mass of about 125 giga-electron volts. This discovery did not introduce mass into the universe. It confirmed that mass had always been there, encoded in the vacuum itself. From a cosmological perspective, the consequences are profound. Once the universe cooled enough for the Higgs field to settle into its current vacuum state, the rules of motion changed everywhere at once. Particles that previously moved like radiation acquired inertia. Reaction rates shifted. The balance between expansion and interaction altered. This transition is known as electroweak symmetry breaking, and it marks one of the most important phase changes in cosmic history. Phase changes are not unfamiliar in cosmology. We observe the recombination era when electrons and protons combine to form neutral atoms, releasing the cosmic microwave background we detect today. We infer inflation, a rapid expansion driven by a field-like energy component early in cosmic time. The Higgs transition belongs in this same category, a global change in the vacuum that restructured the behavior of matter everywhere simultaneously. What makes the Higgs field distinctive is that its effects persist indefinitely. Even today, billions of years after galaxies formed, the Higgs field remains present with the same background value. Every electron in every atom continues to interact with it. Every quark inside, every proton, continues to feel its influence. The stability of matter is not a static property frozen in the past. It is continuously maintained by the vacuum. Observational astronomy indirectly confirms this picture. Stellar evolution models tested against observations from space telescopes such as Hubble and JWST rely on precise nuclear reaction rates. Those rates depend sensitively on particle masses, change the Higgs field's background value even slightly, and fusion thresholds shift. Stars either fail to ignite or burn too quickly. Galaxies either fail to form or collapse prematurely. The fact that long-lived stars exist at all is evidence that the vacuum has chosen a very specific configuration. This raises a challenging question that physics has not fully answered. Why does the vacuum take this value and not another? The standard model can describe the Higgs field's behavior once its parameters are given, but it does not explain why. Those parameters are what they are. Cosmology confronts this limitation directly. A universe with a different Higgs vacuum would not merely look different, it might never produce observers capable of asking the question. Some physicists explore this puzzle through ideas such as vacuum selection, multiverse scenarios, or deeper symmetries beyond the standard model. Others search for answers in precise measurements of Higgs properties, hoping subtle deviations might hint at new physics. What is clear is that the question itself arises only because the Higgs field transforms space from a passive stage into an active participant. In this light, heaviness is not a trait carried by matter like a label. It is an emergent permission granted by the vacuum. Space decides whether particles can linger long enough to bind orbit and build complexity. The Higgs field does not push or pull. It does not exert a force in the classical sense. It simply exists everywhere with a constant value, and that quiet fact reshapes the entire cosmic story. If the Higgs field fills the universe uniformly, why does it treat different particles so unevenly, allowing light to remain weightless while burdening others with mass? If the Higgs field fills all of space, then the most unnerving detail is that it does not treat the inhabitants of that space as equals, because in the same universe where light can cross billions of light years without ever becoming heavy, the carriers of the weak force become so massive that they can barely travel the width of an atomic nucleus before their influence fades. When we claim that a particle has mass, we are not describing a personality trait of matter, and we are not using a metaphor about stickiness or drag. We mean something measurable and repeatable. A massive particle can be at rest. It can store energy as rest energy. It reacts to forces with inertia. Its energy and momentum are related by a different rule than a massless particle. That difference is not philosophical. It shows up in clocks, in accelerators, in the thermal history of the early universe, and in the way stars and plasma behave in space. Now take the Higgs field as a physical fact. The discovery at CERN in 2012 of a Higgs boson with a mass near 125 giga-electron volts provided strong confirmation that the mechanism is real and not a bookkeeping trick. But the Higgs field is not a democratic machine. It does not assign the same mass to every particle by some universal handshake. Instead, each type of particle has its own coupling to the Higgs field, its own strength of interaction with that ever-present background. That single statement explains why the universe can contain both a photon, which remains massless, and a W boson, which is heavy, even though both are fundamental gauge particles and both live inside the same underlying framework of quantum fields. To make this precise without symbols, picture the electroweak theory as a set of rules describing two forces that appear separate at low energies but are unified at high energies. One of these is electromagnetism, carried by photons. The other is the weak interaction carried by W and Z bosons. In the early universe, when temperatures were enormous, the rules did not distinguish them in the way we see today. But as the universe cooled and the Higgs field settled into its present background state, the symmetry of the electroweak theory was broken by the vacuum itself. At that moment, the field configuration of space selected which combinations of the original gauge fields would remain massless and which would become massive. The photon is the result of a special survival. It is not that the photon refuses mass. It is that the photon corresponds to the unbroken part of the symmetry. In the language of the theory, the photon is associated with a gauge symmetry that remains intact after electroweak symmetry breaking. When a gauge symmetry remains exact, the corresponding gauge boson remains massless. This is not a preference. It is a structural requirement of the mathematics confirmed by everything we have ever measured about light. Photons travel at the invariant speed in vacuum. They do not have a rest frame. They do not decay the way massive particles do. Their long-range force, electromagnetism, extends across astronomical distances, shaping plasmas around stars and guiding charged particles through magnetic fields that stretch between planets. The W and Z bosons represent the opposite outcome. Their associated symmetries do not remain intact in the same way once the Higgs field has a non-zero background value. They mix with the Higgs field in a way that produces mass terms, again not as metaphor, but as direct consequences of the coupling between the Higgs field and the weak gauge fields. The results are specific numbers. The W boson mass is about 80 giga-electron-volts. The Z boson mass is about 91 giga-electron-volts. Because they are massive, and because they decay extremely quickly, the weak force becomes short-range. It does not reach across a room. It barely reaches across the interior of an atom. This is why beta decay happens inside nuclei, and why neutrinos can pass through Earth almost unhindered. The weak interaction is real and essential, but it does not build the large-scale architecture of galaxies the way gravity does, and it does not shape everyday electricity and magnetism the way photons do. This contrast between photon and W and Z is one of the cleanest demonstrations that mass is not simply how much stuff a particle contains. The photon is not made of less substance than the W boson. Both are elementary in the Standard Model. The difference is that the W and Z couple strongly to the Higgs field background, while the photon does not couple in a way that generates a mass. The universe is not distributing mass like a resource. It is enforcing a rule about which symmetries remain exact in the vacuum and which do not. How do we know this is not just a story told to make the equations pretty? We know because the predictions were made before the detailed measurements were possible, and then the measurements arrived and matched. In the 1960s and 1970s, theorists such as Steven Weinberg, Abdus Salam, and Sheldon Glashow developed the electroweak theory that required massive W and Z bosons, and predicted specific relationships between their masses and the strength of the weak and electromagnetic interactions. Later in the 1980s, experiments at CERN directly discovered the W and Z bosons and measured their masses. These were not soft conformations. These were hard numbers pulled from collision debris, repeated until the uncertainties shrank. The entire structure became even more convincing when the Higgs boson itself was found, because a Higgs field without a Higgs boson is not a complete quantum theory. The boson is the ripple, the quantized excitation that makes the field a real physical entity rather than a background parameter. Now bring cosmology into the frame, because the universe is the largest laboratory we have, and it ran the experiment long before humans built accelerators. In the first fractions of a second after the Big Bang, the universe was hot enough that particles moved at speeds extremely close to the invariant speed, and many behaved effectively massless because the thermal energies were far above their p, rest mass. In that regime, the difference between massive and massless is blurred in motion, but it remains decisive in reaction rates, in the way expansion competes with interaction, and in the kinds of particles that can remain in equilibrium. As cooling proceeds, masses begin to matter sharply. Massive species become harder to produce, their abundances drop, and the chemistry of the early universe becomes possible only because the inventory of particle masses is what it is. Photons are central to this history because they are the long-lived messengers. They stream freely once the universe becomes transparent, and they preserve information in a way that matter cannot. That is why NASA, ESA, and their partners invest in observatories that detect light across the spectrum. The cosmic microwave background is a bath of ancient photons that reveals conditions when the universe was about 380,000 years old. Telescopes such as JWST capture infrared photons from early galaxies whose light has been stretched by cosmic expansion. None of this would work if photons had a significant mass. A massive photon would behave differently. it would not propagate exactly at the invariant speed. Its dispersion would distort signals over long distances. The range of electromagnetism would not be infinite. Magnetic fields in space would behave differently. The fact that electromagnetic waves travel across intergalactic space with predictable behavior over billions of years constrains the photon mass to be extraordinarily small. The best limits are so tight that for almost any practical purpose, the photon is massless, and in the standard model, it is exactly massless due to the unbroken gauge symmetry. So here is a concrete chain of logic. The universe contains long-range electromagnetism. Long-range electromagnetism requires a massless photon. A massless photon requires an unbroken gauge symmetry. The electroweak theory predicts that after the Higgs field takes on its background value, one combination of gauge fields remains unbroken and becomes the photon. That is why light gets none of this particular mass, while W and Z receive it. The rule is not poetic. It is as mechanical as the fact that a stable bridge must satisfy constraints imposed by geometry and material strength. It is worth pausing on the emotional pressure point that good science sometimes produces, not because it is dramatic, but because it is clean. The Higgs field does not give mass equally. If it did, the world would be unrecognizable. If photons had mass, chemistry would not simply be slightly altered. The very structure of electric fields and magnetic fields would change. If W and Z were massless like the photon, the weak force would be long-range and would disrupt stable nuclei and the balance of reactions that allow stars to shine steadily. The universe we observe, from the spectra of stars to the behavior of plasma around planets, is evidence that nature chose a very particular pattern of couplings. Now we face the deeper and more delicate part of the question. Why do couplings differ? In the standard model, the masses of fermions, such as electrons and quarks, are set by their Yukawa couplings to the Higgs field. Those couplings are inputs. They are measured numbers we plug in, not values predicted from first principles inside the standard model itself. This is one of the honest gaps in our current knowledge. We can describe with stunning precision how different couplings produce different masses. We cannot yet derive why the electron coupling is what it is, why the top quark coupling is so large, or why the neutrino couplings appear tiny compared with the rest. You can view this not as a failure, but as a map marking where the next layer of physics might be hiding. Experiments continue to probe this structure in ways that are directly relevant to cosmology. Every time the LHC measures how often the Higgs decays into pairs of photons, or into pairs of W bosons, or into bottom quarks, it is measuring couplings. It is testing whether the Higgs field behaves exactly as the standard model predicts, or whether it shows deviations that might hint at new fields, new symmetries, or additional Higgs-like particles. Each of those possibilities would reshape early universe behavior, because the electroweak era is sensitive to the field content of nature. A small modification to the Higgs sector could change the nature of the electroweak phase transition. It could alter how matter survived in a universe that should have produced matter and antimatter in nearly equal amounts. This is why the contrast between photon and W and Z is not a narrow technical detail. It is the clearest window into a larger truth. Space is filled with fields. Some of those fields have background values. Those background values break symmetries. Broken symmetries reorganize the particle content of the universe into massless and massive classes. And that classification determines what the universe can do as it cools, expands, and forms structure. A historical story helps anchor the abstraction without reducing it. In the early days of quantum electrodynamics, physicists struggled to compute how light and matter interact without getting infinities. Through relentless work and through the development of renormalization methods, they turned a frightening mathematical mess into the most precise predictive framework in science. Later, when gauge theories were extended to the weak force, the same fear returned in a different form. How can a gauge theory contain massive force carriers without losing consistency? The Higgs mechanism was not invented because it sounded comforting. It was invented because without it, the theory could not be made to behave in a way that matched experiment. The triumph is that a change in the vacuum state of a field solved a problem that looked insoluble, and then the universe itself confirmed it by allowing W and Z bosons to exist with exactly the kinds of masses the theory required. When you look at it this way, the photon's masslessness is not a trivial default. It is a structural consequence of what symmetry remains in the vacuum. The W and Z masses are not arbitrary heaviness. They are the cost of breaking electroweak symmetry in the way our universe breaks it. And the fact that different particles couple differently to the Higgs field is the switchboard that determines the entire hierarchy of masses, from electrons to top quarks, from long-lived atoms to short-lived bosons. And this leaves a final pressure point that fits tightly against what comes next. If the Higgs field can reorganize the universe by changing which particles are heavy and which are not, then the next chapter is unavoidable. Because in the early universe, the Higgs field did not always sit in its current state, and the moment it changed its state was not a footnote. It was a global rewrite of physical behavior everywhere at once. If the Higgs field had always behaved the way it does today, the universe would not merely look different in its earliest moments. It would follow a fundamentally different set of physical rules from the very beginning. To understand why, we have to return to the earliest slice of cosmic history that modern physics can describe with confidence. Observations from missions such as NASA's WMAP and the European Space Agency's Planck satellite tell us that the universe began in an extremely hot, dense state, expanding and cooling from temperatures far beyond anything that can be reproduced on Earth. At those energies, the familiar distinctions between forces and particles did not yet apply in the way we recognize today. In that early environment, the Higgs field did not sit in the calm, settled configuration that now fills space. Instead, it occupied a symmetric, unstable state. In practical terms, this means that the background value of the Higgs field was effectively zero. Without that background value, the mechanism that gives mass to particles could not operate. The universe at this stage was dominated by particles behaving as if they were massless. Energy moved freely. Interactions were rapid. Expansion competed fiercely with every attempt at binding. This was not a gentle condition. It was a universe governed by speed. The idea that the vacuum itself could change over time was once deeply unsettling. In everyday experience, empty space seems timeless and unchanging. But quantum field theory allows and in fact requires that the lowest energy state of a field can depend on temperature and energy density. The Higgs field is a textbook example of this behavior. At very high temperatures, the symmetric state is stable. As the universe cools, that same state becomes unstable, and the field transitions to a new configuration with a non-zero background value. This transition is known as electroweak symmetry breaking, and it occurred when the universe was less than a second old. The exact timing depends on the detailed shape of the Higgs potential, but the energy scale is well established by particle physics experiments. Once the temperature dropped below roughly 100 giga-electronvolts, the Higgs field could no longer remain in its symmetric state. What followed was a genuine phase change, comparable in structure, though not in substance, to the freezing of water or the magnetization of iron. Before the transition, the rules governing particle behavior reflected a higher symmetry. After the transition, that symmetry was broken by the vacuum itself. Nothing external imposed this change. The universe simply cooled into a different state. The consequences were immediate and universal. Before electroweak symmetry-breaking particles such as the W and Z bosons behaved as if they were massless. They could travel long distances, and the weak force they mediate was not confined to tiny ranges. Reaction rates were different, decay pathways were different, The balance between expansion and interaction followed a different logic. Once the Higgs field settled into its new configuration, those same particles suddenly acquired mass. Their range collapsed. Their lifetimes shortened. The weak force became weak not just in name but in spatial reach. This single shift reorganized the entire inventory of particle behavior. From a cosmological perspective, this moment marks the boundary between two universes that obey different effective laws. The equations themselves did not change, but the vacuum state they were evaluated in did. That distinction matters. Physics is not only about equations, it is about which solutions the universe actually inhabits. The importance of this transition becomes clearer when we trace its downstream effects. Once W and Z bosons became heavy, weak interactions slowed. This allowed certain particle species to fall out of thermal equilibrium. Neutrinos decoupled. Quark interactions changed character. The rates at which particles transformed into one another were altered not by decree, but by the inertia introduced through mass. This slowing was essential. A universe that remains forever in a massless regime cannot easily build structure. Energy disperses too efficiently. Interactions do not linger. The electroweak phase transition opened the door to a universe where processes could stretch out in time, allowing complexity to accumulate. In the 1970s, when theorists first explored the electroweak theory in detail, they realized that the Higgs mechanism implied not just particle masses, but a cosmological event. The vacuum of the early universe could not be the same as the vacuum today. That insight linked particle physics to cosmology in a way that had never existed before. The smallest scales and the largest scales were suddenly part of the same story. Decades later, experiments confirmed the particle side of this picture. The discovery of the Higgs boson at CERN validated the existence of the field and its role in mass generation. Cosmology then supplied the time dimension. The universe itself became the record of how that field behaved when conditions were extreme. Modern simulations of the early universe incorporate this transition explicitly. They track how particle populations evolve as the Higgs field changes state. They show how reaction networks reorganize, how decay channels open and close, and how the composition of the cosmic plasma shifts. These models are not speculative exercises. They are constrained by accelerated data, by precision measurements of particle masses, and by astronomical observations of relic radiation and elemental abundances. One of the most striking implications is that the universe did not gradually acquire mass. It switched regimes. Before the transition, mass was effectively irrelevant for many particles. After the transition, mass became a dominant organizing principle. This sharpness is what makes the electroweak phase change such a powerful pivot point in cosmic history. It is also what makes it scientifically dangerous. If the transition had unfolded differently, the universe we observe would not exist in its present form. A transition that occurred too early or too late would alter the balance of interactions. A transition that was too abrupt or too smooth would affect how particles fell out of equilibrium. These details matter because they influence later processes, including the formation of matter over antimatter and the seeds of cosmic structure. Importantly, current evidence suggests that in the Standard Model, this transition was not a violent first-order phase change, but a smoother crossover. That conclusion comes from detailed theoretical studies grounded in measured Higgs properties. The Higgs boson mass, about 125 giga-electron volts, plays a crucial role in determining the nature of the transition. With that mass, the Standard Model predicts a transition that is gentle rather than explosive. This gentleness has consequences. It means that the electroweak transition alone cannot easily explain why the universe contains far more matter than antimatter. That puzzle remains open, and it points toward physics beyond the Standard Model. But the Higgs field still sits at the center of the timeline. Any mechanism that modifies the early universe must pass through the electroweak era and respect the constraints imposed by the Higgs field's behavior. Observational astronomy does not see this transition directly, but it sees its consequences everywhere. The cosmic microwave background, mapped with extraordinary precision by Planck, encodes the conditions of a universe that had already passed through the electroweak transition. The success of Big Bang nucleosynthesis calculations depends on particle masses being what they are. The formation of the first stars, now probed by the James Webb Space Telescope, relies on a chain of physical laws that only make sense in a universe where the Higgs field has settled into its current state. Behind each of these observations is the same quiet fact. Space itself changed its properties early on, and everything afterward followed from that change. There is a historical irony worth noting. When the Higgs mechanism was first proposed, it was designed to fix a problem in quantum field theory. Its cosmological implications were secondary. Yet today, it is impossible to discuss the early universe without it. The Higgs field is not a decorative addition to the standard model. It is the hinge on which cosmic history turns. What remains uncertain is how unique this story is. Could the Higgs field have taken a different path? Could additional fields have modified the transition? Could subtle features of the Higgs potential have left imprints we have not yet detected? These are not idle questions. They motivate future experiments, both at colliders and in cosmological surveys. The early universe does not erase its past completely. It preserves clues in particle properties, in cosmic relics, and in the structure of space-time itself. The Higgs field's early behavior is one of those clues, and it reminds us that the laws we experience today are the outcome of a specific thermal and dynamical history, not an inevitable default. And once we accept that the vacuum itself did not always behave as it does now, a more fragile picture of stability comes into view. The present vacuum may not be the deepest one available, suggesting that what we call permanence could depend on where the universe happens to be sitting in its energy landscape. Why is the Higgs field's background value so specific? And why does 246 giga-electronvolt quietly set the scale of matter? If there were a single number that quietly governed nearly all the heaviness of matter in the universe, the most unsettling thing about it would be that it does not reside in a mountain, a star, or any individual particle, but in the very background of space itself. And that number is 246 giga-electronvolts. It sounds like a number meant for a laboratory, but it does not belong only to accelerators. It is the background value of the Higgs field in the vacuum, what particle physics calls the vacuum expectation value. When people say the Higgs field is everywhere, the important point is not merely that it exists, but that it has a non-zero background level, like a water surface, that already has a set height, whether or not you drop anything into it. This background level is not decorative. It is the control knob that determines the strength of the mass-generating effect for particles that interact with the Higgs field. The Higgs field does not give mass uniformly. Each type of particle interacts with the Higgs background differently. But in this part, we take one more step, and this step matters for cosmology far more than many people realize. Even though each particle has its own interaction strength, the entire system still needs a common background to operate, and that common background is precisely the number 246 giga-electronvolts. If this background value changes, the masses of many particles change with it. And when masses change, nuclear reactions change, chemistry changes, stars change, stellar lifetimes change, and the history of the universe changes. The masses of particles, such as the electron or quarks, are proportional to the strength of their interaction with the Higgs field, multiplied by the Higgs field's background value. You can think of the background value as a basic voltage level of the vacuum, and the interaction of each particle as that particle's sensitivity to this level. If the background level increases, particles with higher sensitivity gain more mass. If it decreases, they become lighter. and even a small shift is enough to throw the material system out of balance. Why is 246 giga-electronvolts special? It is the electroweak scale, the energy scale, at which the electromagnetic force and the weak force were once unified in the early universe, and then separated when the Higgs field froze into its current state. This number did not fall from the sky. It is inferred from quantities measured with very high precision in weak interactions, especially from the Fermi constant, which is determined through processes such as beta decay. Before the Higgs boson was discovered at CERN in 2012, particle physics had already been able to see the shadow of this number through the strength of weak interactions. Much like you cannot see the wind itself, but you can see which way the leaves bend. This is the point many people miss. The universe did not only acquire the value 246 when the Higgs boson was discovered. That number had already been present in the data, like a fingerprint, appearing in many places, from the rarity of certain reactions to the large masses of the W and Z bosons. When ATLAS and CMS announced a new particle around 125 giga-electronvolts that was direct evidence for an excitation of the Higgs field, while the number 246 giga-electronvolts is the CMS background evidence for the vacuum state of that field. There is a clear way to connect the two numbers. The Higgs boson mass of about 125 giga-electronvolts describes the characteristic vibration of the field when it is excited. The 246 giga-electronvolts describes the baseline level at which the field already sits when it is not excited. Together, these two numbers determine the shape of the Higgs potential near the vacuum state. That is, they determine where the field prefers to sit and how it oscillates around that position. When you hear about the shape of the Higgs potential, most of its meaning lies in this pair of facts. The universe does not care about terminology. It operates only on numbers. If the electron were heavier, electron orbits around nuclei would change. Binding energies in chemistry would change. Atomic emission energy levels would change. The absorption and emission spectra that astronomers observe from gas clouds, planetary atmospheres, and star-forming regions would no longer look the same. Part of the work of modern telescopes, including JWST, is to read light spectra, to infer chemical composition and physical conditions at great distances. The fact that we can use the same atomic physics to understand everything from laboratories on Earth to galaxies in the early universe shows that the background constants, including the Higgs background value, have remained stable over cosmic time after the electroweak era. If quark masses change, the consequences run even deeper. The masses of protons and neutrons are not simply the sum of the masses of their constituent quarks. Most of the nucleon mass comes from QCD binding energy from gluon dynamics and the relativistic motion of confined quarks. But quark masses still matter because they affect the energy difference between protons and neutrons and change how the strong force arranges nucleons inside nuclei. A small difference between proton and neutron masses is why the proton is stable. A free neutron is unstable, and neutrons inside nuclei can be stable. If you change these differences, you change the entire isotope map. You change fusion reactions in stars. You change Big Bang nucleosynthesis, and you change the amounts of helium and deuterium formed very early. These are things cosmology has tested for decades through astronomical observations. One way to sense this sensitivity is to look at stars. Stars exist because of a balance between inward gravitational pull and outward pressure from heat generated by nuclear reactions. The stellar core temperature must reach a threshold for nuclei to overcome electrostatic repulsion and fuse. That threshold depends on nuclear charge and nuclear structure depends on the masses and interactions of fundamental particles. If the electron were significantly heavier, atomic structure would change. If the proton-neutron mass difference changed, the chains of energy-producing reactions in stars would change. The extreme result could be stars that are much harder to ignite, or stars that ignite too easily and burn their fuel too quickly. A universe with very short-lived stars would not have much time to produce heavy elements and distribute them across stellar generations. In our universe, you observe stars with lifetimes of billions of years, galactic disks that remain stable for long periods, and molecular clouds that form stars cyclically. All of this indirectly shows that the fundamental control knobs are not significantly off, and that the Higgs background value lies within a range that allows long-term structure. There is a historical story worth remembering here because it shows that the number 246 giga-electron volts is not a post-hoc invention. In the second half of the 20th century, as electroweak theory was completed, physicists realized that to describe the weak force with a gauge theory, while maintaining consistency, the W and Z bosons had to acquire mass in a way that did not break gauge symmetry at the level of the equations. The Higgs mechanism resolves this by allowing the vacuum to carry a background configuration. From this, the electroweak scale can be inferred, and that scale matches the strength of weak processes measured in decays. They had not yet seen the Higgs boson, but they had already read the background information of the field. If you want a short statement that captures the spirit of testable science, Richard Feynman's line is often quoted because it is blunt and unadorned. "What I cannot create, I do not understand." This sentence is not decorative. It reminds us that understanding in physics means being able to build a model that produces quantitative predictions and can be tested. For the Higgs field, creating here means constructing a theoretical framework that predicts the masses of the W and Z bosons, predicts the relationship between the electroweak scale and weak processes, and ultimately predicts the existence of the Higgs boson as an excitation of the field. The crucial point is that these predictions were brought into the laboratory and measured. Why is the number 246 giga-electronvolts so precisely right for the universe to have chemistry, stars, and structure? Current physics describes it, but does not yet explain its deepest origin. In the standard model, you input the parameters of the Higgs potential and obtain the background value. Those parameters are measured from nature. But the question, why is it that value remains open? And precisely because it remains open, it drives both particle physics and cosmology. What is striking is that this number does not affect only electrons or quarks. It sets the entire electroweak scale. And because the electroweak scale determines the masses of the W and Z bosons, it determines the range and strength of the weak force. The weak force is not merely a force in textbooks. It governs beta decay, meaning it governs the conversion of protons into neutrons, and vice versa in many environments. That affects neutrino emission in stellar cores, affects nuclear balance in massive stars, and affects how elements are synthesized. In the early universe, the weak force determines when neutrinos decouple from the plasma, and that influences the effective radiation energy density at early times, which can leave imprints in cosmic microwave background data and large-scale structure. In other words, the Higgs background value is a control knob sitting at the intersection of the microscopic and the macroscopic. You measure it using microscopic data, and then you see its macroscopic consequences through the thermal history of the universe and through stellar physics. These connections are why modern cosmology cannot be separated from particle physics. If one must express this with a scientific image, one can use the image of a mold. The Higgs background value is like a fixed mold size, and each particle has its own degree of interaction with that mold. The mold does not create matter, but it determines the size of the output. When the mold changes, all sizes change. In the universe, these sizes are not geometric, but masses, force ranges, and reaction rates. And then we reach an even more pressing point. Even though the Higgs background value is stable today, that does not automatically mean this state is the lowest possible state of the universe. The shape of the Higgs potential, together with parameters such as the Higgs mass and the top quark mass, may place the universe in a region where the current vacuum is only metastable. This is not a settled conclusion, but it is a story being tested with increasingly precise measurements. And if the universe truly lies near the boundary between stability and metastability, then the number 246 giga-electron volts is not only the scale of matter, but also an indicator of how safe the vacuum configuration on which everything rests actually is. And precisely because that number carries so much weight, another difficulty follows almost immediately. If the Higgs field sets the scale of matter itself, then observing the Higgs boson becomes an unusual task. What experiments are trying to detect is not a stable object, but a fleeting disturbance of that background. Something that exists for such a brief interval that it cannot be seen directly, only reconstructed from the traces it leaves behind. Why did it take nearly 50 years to catch the Higgs? And why does its lifetime feel like the universe hiding evidence on purpose? What makes the Higgs most frustrating is not that it is hard to understand, but that it exists in a way that disables almost every familiar scientific sense, because the thing called the Higgs boson appears and disappears so quickly that you never actually see it. You only see the fragments it leaves behind, and you must prove its existence in reverse. Like a court case, with no eyewitnesses. In modern particle physics, seeing does not mean seeing with the eyes. Seeing means a measurable trace in a detector, repeated often enough with background probabilities understood well enough that you can say a new cause has appeared in the data. The Higgs belongs to the class of objects that makes this definition as strict as possible. It does not produce a long track like a muon, nor does it leave an easily recognizable ionization trail. It is produced in high-energy proton-proton collisions and then decays almost instantly into other particles. You hunt the Higgs by hunting its decay channels, such as 2 photons, 4 leptons, or other combinations, and then looking for a peak in the invariant mass distribution reconstructed from the decay products. Why did it take nearly 50 years? The first reason is energy and probability. The Higgs is not something you produce easily. To produce a Higgs, you need sufficiently high collision energy and sufficiently high beam luminosity to collect a rare number of events. Accelerators had to reach energy and intensity regimes that previous generations could not access. The LHC was that leap. When the LHC operated at proton beam energies of several tera-electron volts and achieved high enough luminosity, a new door opened for processes with small but non-zero probabilities. The second reason is background noise. Even when a Higgs is produced, most of its decay channels are buried in a sea of standard processes that generate similar final states. 2 photons can arise from many background mechanisms. 4 leptons can arise from other electroweak processes. To extract the Higgs from the background, you must understand the background so well that systematic uncertainties do not generate a fake peak on their own. This is why experiments cannot rely on a single channel. They must use multiple independent channels, multiple event selection strategies, multiple background models, and require consistency across analyses. The third reason is resolution and calibration. To see a peak around 125 giga-electron volt in the 2 photon channel, the detector must measure photon energies with great precision, understand the calorimeter response, and calibrate it over time, position and operating conditions. In the 4-lepton channel, you must measure electron and muon momenta with extreme accuracy, understand the magnetic field, the material, and every small bias in track reconstruction. These tasks are not the beautiful part of the story, but they are precisely what turns an observation into a discovery. When you hear about the 4th of July 2012, what matters is not just a crowded seminar. It was the moment when two independent experiments, ATLAS and CMS, presented evidence reaching 5 sigma statistical significance around a mass of about 125 giga-electron volt. In other words, a probability so small that random background fluctuations could mimic the signal that the community accepts it as a discovery. CERN announced this in an official statement which clearly quoted CMS spokesperson Joe Incandela. The results are preliminary, but the 5 sigma signal at around 125 giga-electron volt we're seeing is dramatic. This is indeed a new particle. That sentence is like a signature at the end of a case file, but it also strictly follows scientific discipline. Preliminary is not a way of downplaying the result to avoid attention. It is the correct language of an experiment, standing before a major result and knowing that every detail will be scrutinized. You can hear two things coexisting in that sentence. First, enough confidence to make a declaration. Second, enough caution not to go beyond the data. And it is precisely this balance that gives the discovery lasting value. The number 5 sigma is often repeated like a slogan, but its true meaning is a protective barrier against statistical illusion. LHC data are data of probability. Billions of collisions generate countless combinations. If you look long enough, in enough channels, you are almost guaranteed to see random ripples that resemble a signal. 5 sigma is a demanding threshold to ensure that this is not merely such a ripple. CMS also stated very clearly on its summary page about the observation of the new particle at 125 giga-electron volt that they observed an excess of events with a statistical significance of 5 standard deviations. 5 sigma above background expectations. The Higgs boson is not only hard to produce, it also lives an extremely short time. The lifetime of the Higgs is not measured with an ordinary clock, but inferred from its decay width from how the signal spreads around the central mass. CMS has a dedicated article on the Higgs lifetime and gives a value on the order of 10 to the power of negative 22 seconds, with a central estimate of a few times 10 to the power of negative 22 seconds. 10 to the minus 22 seconds means 1/10,000th of a trillionth of a billionth of a second, so short that even light in vacuum travels only a few % of a femtometer, in that time smaller than the characteristic size of an atomic nucleus. In other words, the Higgs disappears before any journey can begin. It leaves no track. It leaves only decay outcomes. So how do we know the Higgs existed if all you measure are photons, electrons, muons, or hadronic jets? You must do something very specific to high-energy physics. Reconstruct an unseen particle from what is seen using conservation of energy and momentum. You take the energies and directions of 2 photons and compute a quantity corresponding to the mass of the object that produced them. You do this for millions of events. If there were no Higgs, the distribution would be smooth with a background that falls gradually with energy. If there is a Higgs, there will be a small, narrow peak at the right position, with the right width repeating across multiple analyses. What makes the story resemble an investigation is that you are always confronted with false suspects. 2 photons can come from many standard processes. 4 leptons can come from a Z-boson pair. Jets can fake B quarks. This is why the Higgs hunt is not only about increasing energy, but about increasing discrimination power. That is why the ATLAS and CMS detectors are designed as multi-layer systems, with trackers, electromagnetic calorimeters, hadronic calorimeters, and muon systems, so that a single event is viewed through many independent measurements. Each layer has its own function, and agreement among layers reduces confusion. There is a detail that often surprises listeners in the proper scientific sense. The Higgs does not appear by itself like an ordinary particle. It is typically produced through interactions of other fields in collisions, for example through gluon-gluon fusion, where two gluons inside the proton form a quantum loop with heavy quarks, mainly the top quark, and then produce a Higgs. This means the Higgs is both a new particle and a window into quantum loops that cannot be seen directly. When you measure Higgs production rates and decay branching ratios, you are also probing the underlying quantum field structure of nature. And this is why the story lasted nearly half a century. In 1964, the Higgs mechanism was proposed to resolve a contradiction in gauge theory, how weak force bosons could have mass while preserving consistency. But going from a mechanism on paper to a particle seen in data required an entire chain of technology. You needed stable superconducting magnets, large-scale cryogenics, proton beam control, real-time trigger systems, massive data storage and processing, and rigorous statistical analysis. No link in the chain could be weak. A miscalibration or an incorrect background model could create a fake Higgs or cause you to miss the real one. Placed in the broader context of observational science, there is an interesting parallel. NASA and ESA are accustomed to proving the existence of objects they cannot touch by reading their imprints in light spectra and motion. You do not touch an exoplanet, but you measure the dimming of a star as the planet transits. You do not touch dark matter, but you measure gravitational lensing and orbital motions. Particle physics does the same thing, but at a much smaller scale. You do not see the Higgs. You see its imprint in the statistical distributions of decay products. This way of thinking connects cosmology and particle physics through the same discipline, indirect measurement, cross-checks, and only then conclusion. A challenging question often arises here and deserves to be posed carefully. If the Higgs lives such a short time, could there be new phenomena associated with the Higgs that we have missed because of current measurement methods? The answer cannot be definitive, but the scientific reasoning is clear. First, the Higgs is tested through many decay channels and production modes. If there were large deviations, they would typically appear as inconsistent branching ratios or altered spectral shapes. Second, there are still properties that are difficult to measure, especially the Higgs self-coupling, which determines how the Higgs interacts with itself and shapes the Higgs potential. That is a region where current data are limited, and one reason the community discusses future accelerators. The 2012 discovery did not end the Higgs story. It merely confirmed that there is a boson consistent with the Higgs in the standard model. The next chapter is to test whether it is truly the standard Higgs or just part of a broader structure with additional fields, particles, and dynamics at higher energies. And the test is not done by intuition, but by more precise measurements of couplings, decay widths, and rare processes. One point must be stated clearly to avoid a common misunderstanding. The Higgs's extremely short lifetime is not the universe intentionally hiding anything. It is a direct consequence of the fact that the Higgs has many kinematically and symmetry-allowed decay channels. The more decay pathways a particle has, and the more strongly it couples to final states, the faster it decays. This is a general mechanism in particle physics. What makes the Higgs special is that it sits exactly at a point where important channels open and backgrounds are large, turning its discovery into a test of both technology and statistics. When you hear again the phrase 5 sigma signal at around 125 giga-electron-volt is dramatic in the CERN announcement. It is not merely the emotion of a summer day in 2012. It is the summary of decades spent building machines, building detectors, and building analysis methods to catch a ripple that existed for about 10 to the power of negative 22 seconds. And once that ripple was caught, scientific pressure immediately shifted direction. Because if the Higgs leaves only traces and then disappears, the next question is no longer does it exist, but what is the true shape of the Higgs potential, and whether the numbers we measure place the universe in a truly stable state, or merely a long-lived metastable one? Why does the Higgs field threaten to redefine what stable universe even means? If there is one thing that makes the concept of a stable universe uncomfortable enough to require rethinking from the ground up, it is that the numbers we measure for the Higgs boson and the top quark appear to place the entire current vacuum of the universe right at the boundary between stability and mere metastability. In the previous parts, the Higgs field appeared as the background of space, setting the mass scale of matter and determining the short range of the weak force. In this part, the story moves into a region that is less intuitive, but fully testable by calculation and measurement. It begins with a highly technical question that has very broad consequences. When we say that the Higgs field has a vacuum state, we mean that it has a low-energy configuration in which the universe is currently sitting. The problem is whether the low-energy state the universe occupies is the absolute lowest state or not. In quantum field theory, the energy of the vacuum is not a single fixed number that remains invariant at all energy scales. When you look at higher energy scales, the parameters of the theory change in a way that can be calculated using renormalization group running. This means that the shape of the Higgs potential, that is how the energy depends on the value of the Higgs field, can gradually deform when you consider configurations where the Higgs field has very large amplitudes. And it is precisely here that the top quark enters with a special role. The top quark is the heaviest fermion in the Standard Model, and the strength of its interaction with the Higgs field is very large. This interaction does not merely determine the mass of the top quark, it also contributes strongly to how the Higgs self-interaction parameter evolves with energy scale. The striking result from 2-loop and 3-loop analyses developed by the community after the discovery of the Higgs boson is that there may exist a very high energy scale at which the effective curvature of the Higgs potential changes sign. Put into words, if you push the Higgs field away from the region near its current background value to extremely large amplitudes, the energy may not continue to increase like an infinitely deep bowl. It may instead form a lower region far away, making the state the universe occupies only a shallow valley rather than the deepest minimum. When such a situation exists, we call the current vacuum metastable. This term has a very specific meaning in field theory. It describes a state that appears stable in all current experiments, and observations can persist for far longer than the age of the universe, but in principle still has a probability of transitioning to another vacuum state with lower force. Energy through a quantum mechanism. This mechanism is often described as the nucleation of a bubble, a very small region that randomly transitions to the lower energy vacuum configuration, and then, if conditions are right, can expand at an extremely high speed. This is a conclusion of the form. If you take the numbers and extrapolate the Standard Model to high scales, then this follows not a claim that such an event will certainly occur. The most unsettling point is that the currently measured numbers seem to place us near the boundary. In a Physics Today article on the future of the Higgs, Joseph Licken wrote a sentence that became a reference point in the community because it stated the issue directly. Strikingly, the measured Higgs and top quark masses put the universe right at the edge of the stability versus metastability divide. In the same text, he also noted that if one plugs in the numbers in a straightforward way, one inferred scenario is that an extremely rare quantum fluctuation could produce a different vacuum bubble that spreads at nearly the speed of light, accompanied by time estimates on the order of 10 to the fourth power of 100 years. Phrases like right at the edge and such enormous timescales are not meant to shock. They reflect two things at once. First, the genuine sensitivity of the conclusion to the measured parameters. Second, the fact that even if the vacuum is metastable, it can still live for an extraordinarily long time compared to any familiar astronomical timescale. To understand why the conclusion is so sensitive, you do not need symbols, only a clean chain of reasoning. The shape of the Higgs potential at low energies is anchored by accelerator measurements, especially the Higgs boson mass of about 125 giga-electron-volt and its couplings. When you extrapolate to higher energy scales, the Higgs self-interaction parameter can gradually decrease. The top quark drives this downward trend because the top Yukawa interaction with the Higgs pulls that parameter down. If the self-interaction parameter becomes negative at some scale, we say that the standard model under this extrapolation suggests metastability. Modern analyses often show that the scale at which it changes sign can be approximately between 10 to the power of 10 and 10 to the power of 11 giga-electron-volt, depending on the value of the top mass and its uncertainties. What is noteworthy is that this scale is far beyond the energies of the LHC. This means we are using data at the scale of hundreds of giga-electron-volt to infer the behavior of the theory at scales billions of times higher. For this reason, the correct way to speak always includes explicit assumptions, and the way to test the picture is to pursue increasingly precise measurements. Here, the top quark mass becomes a crucial node, not only because the top quark is heavy, but because the value of the top mass enters directly into the calculations of how parameters run with energy scale. Small changes in the measured top mass can shift the conclusion back and forth between absolute stability and metastability. Review articles and detailed analyses have emphasized this point for many years because the uncertainty in the top mass measurement is not merely a technical detail, but the factor that determines the boundary. There is a story behind the measurements that makes this point easier to grasp. The mass of the Higgs boson is not weighed directly like a physical object. It is reconstructed from its decay products in ATLAS and CMS, and then combined across many channels to achieve precision. The same is true for the top quark mass. The top quark decays almost immediately, leaving jets and leptons, and the top mass is inferred from reconstructed quantities across millions of events with sophisticated systematic corrections. A small shift in jet energy calibration, in the modeling of hadronization, or in the description of the detector, can influence the inferred top mass value. This does not make the measurements unreliable. It explains why the community must continuously refine measurement techniques and report uncertainties rigorously. When cosmologists talk about the fate of the universe, they often refer to expansion, dark energy, dark matter, and structure formation. Here, the story does not begin with space-time geometry, but with the structure of the vacuum in the standard model. If the electroweak vacuum is metastable, then stability is no longer an absolute statement. It becomes a probabilistic description with an extremely long lifetime. Importantly, we see no observational signs indicating that the vacuum is on the way to a phase transition. The observed universe, from the cosmic microwave background to galaxy spectra, remains consistent with a thermal history and a set of physical constants that have been stable for billions of years. Serious metastability models also typically conclude that the expected lifetime of the vacuum is vastly longer than the current age of the universe. The correct interpretation, therefore, is that we are dealing with a boundary-type conclusion, sensitive to parameters that could change with better data, or with the appearance of new physics at high scales. New physics is a point that cannot be ignored. The entire metastability conclusion depends on the standard model being valid up to extremely high energy scales that we cannot yet test directly. If new particles, new symmetries, or new interactions exist at intermediate scales, they could alter how the Higgs potential runs with energy and potentially stabilize it. Many studies have explored such scenarios in various forms, from extensions of the Higgs sector to additional scalar fields or effects at the Planck scale. This means that even if metastability is correct, under standard model extrapolation, it is not automatically the final word on the universe. Still, there is one point worth keeping in mind because it captures the right-on-target feel of science. Metastability is not an isolated idea. It connects directly to quantities measured at the LHC, especially the Higgs mass and its couplings. It connects to a specific particle, the top quark, which we also measure. It connects to renormalization group methods that have been tested in many contexts. And it produces a phase map in parameter space where changing values by only a few % can shift the picture to absolute stability or instability. Joseph Licken captured this spirit when he wrote that if the Higgs were a few % heavier, or the top quark a few % lighter, the vacuum would be stable. A challenging but necessary question here is whether being near the boundary carries deeper meaning or is merely accidental. We do not need to answer it. What can be said with confidence is that being near the boundary turns the Higgs into a cosmological measurement in a broad sense. It turns collider numbers into information about vacuum structure at extremely high energy scales. And it makes precision measurements, especially of the top mass and the Higgs self-coupling, in the future key to narrowing the story. Absolute stability means that the Higgs potential does not produce a lower state at any field amplitude within the domain where the standard model applies. Metastable means that a lower state may exist, but the transition probability is so small that the lifetime far exceeds the age of the universe. Unstable means that the probability is large enough that the universe could not have existed as long as it has. Modern analyses usually place us in the metastable but extremely long-lived region near the line separating metastability from stability. And once you accept that the vacuum may contain a story about stability or metastability, a new pressure immediately appears in the broader direction of cosmology, because the Higgs field carries energy even in empty regions, and that collides directly with the question of why the vacuum energy, inferred from the accelerating expansion of the universe, is so astonishingly small. The most troubling aspect of the Higgs field at the level of cosmology does not lie in particle masses, but in a seemingly secondary detail. Even when no particles are passing through it, the Higgs field still carries energy of its own. That energy should, in principle, leave a huge gravitational imprint on the expansion of the universe. Yet the observed universe expands with only a very mild acceleration. We begin with observational facts, because this is where cosmology stands on its firmest ground. Since the late 1990s, observations of distant type Ia supernovae have shown that the expansion of the universe does not slow down as one would simply expect from the gravitational pull of matter, but instead shows signs of acceleration, a result associated with a positive cosmological constant or some form of dark energy. Many subsequent independent measurements, including data from the cosmic microwave background and large-scale structure, have reinforced the standard picture in which most of the universe's current energy density resides in a component collectively called dark energy. NASA has described this succinctly. Several billion years after the universe began, its expansion started to accelerate, and the name dark energy is used for the unknown agent behind that effect. Now place alongside this observational fact a truth from quantum field theory. A field, even in the absence of particle excitations, can still possess energy in its vacuum state. The Higgs field is such a field, and more specifically, the Higgs field not only has quantum fluctuations around a background level, but also has a non-zero background itself. That background level, the vacuum value of the Higgs field, has appeared throughout the previous parts because it sets the electroweak scale and determines the masses of many particles in the standard model. If the Higgs field has a vacuum configuration, then that configuration has energy. In general relativity, energy is not merely a bookkeeping number, it is a source of gravity. A uniform vacuum energy density acts like a cosmological constant, meaning it directly affects the rate of cosmic expansion. And here, two worlds collide. The world of particle physics says that the vacuum is not empty. The world of cosmological observation says that if there is vacuum energy, then the effective value inferred from the acceleration of expansion is extraordinarily small by particle physics energy standards. This is precisely the cosmological constant problem, one of the greatest tensions between quantum field descriptions and gravitational descriptions of the universe. Classic review articles on the subject emphasize that when one naively sums vacuum energy contributions from quantum fields, the resulting values are absurdly large compared with the value inferred from cosmological observations. The important point is that the wording must be careful. No one claims that this naive estimate is a complete calculation because quantum field theory and gravity involve renormalization procedures and questions about the absolute meaning of energy. But the gap between expectation and observation is too large to ignore, and the Higgs field provides a concrete example that makes this mismatch non-abstract. Let us express this in operational language without symbols. If you have a large vacuum energy density, the universe will be driven to expand with strong acceleration. The acceleration will not be gentle in the way inferred from supernova data, the cosmic microwave background, and large-scale structure. Conversely, if the effective vacuum energy density is very small, the acceleration will be weak, and that is essentially what we see in present data, where the LECDM model fits many observations very well. So the question lies here. In the particle physics picture, the Higgs field has a vacuum configuration at the electroweak energy scale. Why does the contribution of that configuration not make dark energy overwhelmingly large? To see the pressure more clearly, recall a point. The Higgs field has a characteristic background level, and the electroweak scale lies around hundreds of giga-electron volts. This is a very large energy scale, compared with the energy scale associated with dark energy, as inferred by cosmology. You do not need precise numbers to grasp the contrast. On one side is the energy scale of colliders and the weak force. On the other side is the energy scale of the present cosmic acceleration. One side involves hundreds of giga-electron volts. The other reveals itself only when you measure the universe over billions of years and billions of galaxies. The Higgs field thus becomes a special point of contact. It is the only quantum field in the Standard Model whose excitation, the Higgs boson, we have directly observed. And at the same time, it possesses a background configuration. We are not talking about a hypothetical field. We are talking about a field that colliders have confirmed through a new particle around 125 giga-electron volt. And it is precisely this confirmed field that poses an unavoidable question about vacuum energy. An important step is to distinguish two notions that are often conflated. One is the vacuum expectation value of the Higgs field, which determines particle masses through couplings. The other is the effective vacuum energy density that influences cosmic expansion. These two are related but not identical. You can have a field with a non-zero background whose contribution to the total vacuum energy is cancelled by opposing constants in the theory or absorbed into the definition of the cosmological constant. But if such cancellation occurs, it brings us straight back to the core of the problem. Why do large contributions from many different fields cancel almost perfectly, leaving a tiny remainder equal to the observed value? Here, we must keep the narrative rhythm like an investigation, because that is exactly what it is. Cosmology has no way to weigh the vacuum directly. It only sees its gravitational consequences. Particle physics has no way to measure absolute vacuum energy with a detector. It measures energy differences and dynamical effects. The two fields are looking at the same thing from different sides, with different instruments. And the gap between those perspectives is precisely where the problem persists. There is a chain of observational data that prevents this investigation from being dismissed as a side issue. Planck data on cosmological parameters within the LSCDM model show that a model with a cosmological constant-like component describes many observations extremely well, and there is as yet no compelling evidence that the model must be extended in most standard tests. At the same time, NASA and many large survey programs continue to measure dark energy because the question of its nature remains open. Recently, results from DESI have been widely discussed because they suggest the possibility that dark energy may not be strictly constant in time, although the statistical significance is still being examined by the community. If dark energy truly varies, the vacuum energy story becomes even less something that can be treated as a single fixed constant to be tuned. Within this picture, the Higgs field becomes unavoidable evidence. It reminds us that even in the simplest standard model, the vacuum already has structure. And if the vacuum has structure, we cannot treat dark energy as a mist entirely disconnected from particle physics. At the very least, we must ask what familiar fields contribute to the background energy, how they contribute, and why the effective contribution is small. A challenging question to pose here is whether the Higgs field itself could be used to explain dark energy. Caution is required. The Higgs field has a background level, but fluctuations around that level correspond to the Higgs boson, with a large mass and a heavy scalar field typically does not produce a slowly varying dark energy compatible with the current acceleration. Moreover, collider measurements tightly constrain the properties of the Higgs, making any direct repurposing of the Higgs as a dark energy field difficult. Even so, the Higgs remains relevant because it is the clearest example of a field with a non-trivial vacuum, and it highlights the renormalization question of vacuum energy in a theory that combines quantum fields and gravity. Another line of argument is to view the cosmological constant problem as a sign that the standard model is not the final layer. There may exist new symmetries that make vacuum energy cancel more naturally. There may be dynamical mechanisms that render the effective value small. There may be corrections from quantum gravity that we do not yet understand. But in every direction, the Higgs field remains an experimental anchor. It is a field we know exists. It has a background. It has a potential, and we measure part of the shape of that potential through the Higgs mass and its couplings. Consider one more cosmological datum that the JWST has helped bring back into focus in recent years: measurements of the present expansion rate and the Hubble tension. Analyses based on Cepheid stars and supernovae observed with Hubble and JWST have reinforced that the expansion rate inferred from the local distance ladder is higher than that inferred from the CMB within the standard model prompting renewed questions about dark energy or early universe physics. When a cosmological model shows such internal tension, every background component, including how we understand vacuum energy, becomes a place that deserves closer scrutiny. However, it is important not to overstate the data. So far, a model with dark energy resembling a cosmological constant still describes a large body of observations well, and suggestions of variation from DESI or other surveys require more data and independent checks. Therefore, the correct framing is to treat this as an unresolved collision point, not as a conclusion about the fate of the universe. The Higgs field gives us a structured vacuum at the electroweak scale. Cosmology gives us a very mild, accelerated expansion attributed to dark energy. If dark energy is vacuum energy, then the effective vacuum energy must be extraordinarily small compared with familiar quantum field energy scales. This mismatch is the cosmological constant problem. The Higgs field does not solve the problem, but it makes it impossible to avoid, because it is a real field, experimentally confirmed, living directly in the vacuum that cosmology is measuring. And once you see the Higgs field as part of the vacuum energy question, a further pressure becomes hard to escape. If background energies of fields can influence cosmic history, then the Higgs phase transition in the early universe itself may have affected how the universe selected matter over antimatter in some way. Even though current data do not yet allow a firm conclusion, what makes the story of the existence of matter most unsettling is not that the universe produced particles, but that if the laws treated matter and antimatter fairly, then after the first collisions, everything should have annihilated itself, completely leaving behind an almost empty sea of photons. Yet here you are, in a universe filled with protons, electrons, atoms, stars, and galaxies. Modern observations state very clearly that the universe has a small but persistent asymmetry between baryons and photons, often summarized by a baryon-to-photon ratio of a few parts in a billion, a number inferred consistently from cosmic microwave background data and independent checks. This number is extremely small when compared with the particle density of the early era, but it is enormous when compared with a universe with no stable matter, because even such a tiny leftover fraction is sufficient to build all the structures we see today. From an investigative perspective, the question is not whether the universe created particle-antiparticle pairs. It certainly did, because high temperatures convert energy into particles through every allowed channel. The question is how a small excess of matter survived after most matter and antimatter annihilated each other. If one wants a minimalist logical framework, the community usually returns to the three famous conditions proposed by Andrei Sakharov in 1967. Baryon number violation is required. Violation of C and CP symmetry is required. And a departure from thermal equilibrium is required. These three conditions are not a solution formula, but they are a filter. Any mechanism that generates an asymmetry must pass through those gates in one way or another. Now the Higgs field enters in a very specific way, because the Higgs field controls how the universe undergoes a phase transition at the electroweak scale. We said in part 3 that the early universe experienced electroweak symmetry breaking when the temperature dropped to around 100 giga-electron volts. At that scale, the Higgs field changes its vacuum state. The W and Z become massive, and the weak force becomes weak in the sense of having short range. This is not merely an internal event of particle physics. It is a timestamp in the thermal history of the universe. If the electroweak phase transition is strongly first order, meaning it proceeds through the formation of bubbles of a new phase within the old one, then you have a natural environment for generating non-equilibrium conditions. Think of it operationally. As the new phase bubbles expand, there is a bubble wall where the Higgs field changes in space over a very small region. Particles in the plasma passing through that region experience different physical conditions before and after. If in this process there is sufficient CP violation, certain reactions can produce a small difference between the number of particles and antiparticles. And if at the same time baryon number violating processes are active, you can freeze in a baryon asymmetry as the new phase fills space. In the standard model, the key baryon number violating process at the electroweak scale is the sphaleron, a non-perturbative effect of gauge theory that allows transitions between different field configurations and leads to changes in baryon and lepton number according to specific rules. Lattice calculations have studied the sphaleron rate in the electroweak crossover region with a Higgs mass of 125 giga-electron volt, because this rate determines whether an asymmetry, if created, is washed out or not. This is a very exacting line of reasoning in early universe physics. You do not just need to create an asymmetry, you also have to protect it from being erased. Theoretical results and non-perturbative simulations show that in the standard model, with a Higgs boson of about 125 giga-electron volt, the electroweak transition is not strongly first order, but rather a crossover, meaning the transition proceeds more smoothly without sharp bubble walls. and without producing a sufficiently strong non-equilibrium environment in the way classical electroweak baryogenesis requires. Put briefly, the Higgs in the Standard Model is too heavy to allow a strong first-order transition. This conclusion appears in many reviews and analyses after the Higgs was discovered, because the measured Higgs mass immediately narrowed the model space for minimal electroweak baryogenesis. So why do we still say that the Higgs decides whether the universe could prefer matter? Because the Higgs sets the boundary conditions for the entire electroweak baryogenesis scenario. If the phase transition is not strong, you lack a sufficiently clear non-equilibrium ingredient. If CP violation in the Standard Model at the relevant temperatures is too small to generate the required amount of asymmetry, you lack the second ingredient. And if sphalerons remain strongly active in the crossover region, they can erase what you try to create. The conservative conclusion of the community today is usually that the Standard Model alone struggles to generate the observed baryon asymmetry through electroweak baryogenesis, and therefore, if an asymmetry was created at the electroweak scale, new physics is required, often involving an extended Higgs sector, additional scalar fields, or new sources of CP violation. There is a historical story that clarifies why this became a forensic timeline. Before the Higgs was found, electroweak baryogenesis was an especially attractive direction, because it directly linked a cosmological question to physics at a scale testable by colliders. You did not need to go to the gut scale. You only needed the electroweak scale. Many models in the 1990s and early 2000s attempted this, such as in the context of the MSSM, where new particles could strengthen the phase transition and enhance CP violation. But when the Higgs was measured around 125 giga-electron-volt, many regions of parameter space, in models relying on simple thermal effects, became strongly constrained. From then on, the Higgs era became an investigative milestone. If the asymmetry cannot be generated here within the Standard Model, then either it was generated by new physics still tied to the Higgs, or it was generated earlier by a different mechanism. That other mechanism is leptogenesis, an idea in which a lepton asymmetry is generated first, and sphalerons then convert part of that lepton asymmetry into a baryon asymmetry, before sphalerons shut off as the universe cools. This is why the sphaleron rate at the crossover remains important, even if one is not doing electroweak baryogenesis in the narrow sense. From an investigative standpoint, the Higgs still sits at the center of the file because it determines the timing of electroweak symmetry breaking and determines when sphalerons become sufficiently suppressed to lock in the asymmetry. A challenging question that is often asked is where the traces of new physics might lie if the Standard Model is insufficient. A careful way to state it is this: new physics could make the phase transition strongly first order by altering the shape of the Higgs potential at high temperature, or by adding a light scalar field that mixes with the Higgs, or by generating effective interactions that strengthen the Higgs self-interaction at the dot transition temperature. These changes cannot be arbitrary, because colliders have already measured many properties of the Higgs at low energies, and any model must simultaneously fit LHC data. As a result, this becomes a double constraint problem. Cosmology demands enough strength to generate the asymmetry. Colliders demand enough subtlety to avoid spoiling existing measurements. If you want a strong phase transition, you usually need the high-temperature Higgs potential to have two separated preferred regions divided by an energy barrier, so that bubbles of the new phase can form in the old one. If the transition is only a crossover, the preferred region slides continuously without forming sharp bubble wall. A Higgs mass of 125 giga-electron-volt, when inserted into non-perturbative calculations, leads to a crossover picture in the Standard Model. As for CP violation, it is known that the Standard Model contains CP violation in the CKM matrix. and this is sufficient to explain certain meson decay phenomena. But many analyses show that this level of CP violation is far too small to generate the observed baryon asymmetry through electroweak baryogenesis. This is one of the reasons this mechanism often requires new CP sources, for example, in an extended Higgs sector. What keeps the story compelling is not a vague promise, but the reality that this is one of the few problems where a particle discovered at a collider carries direct consequences for a foundational question about the universe. When you measure the Higgs mass, you do not just add a number to a table. You alter the structure of the possibilities for generating an asymmetry at the electroweak scale. When you measure the top quark and the couplings, you change the details of how the potential runs with temperature, and you change the model space for the phase transition. When you measure the Higgs self-coupling in the future, you will directly probe the shape of the potential, which determines whether the transition is strong or weak in extended models. And there is still a layer of cosmological observation underlying the entire story. Any baryogenesis mechanism must generate exactly the level of asymmetry suggested by CMB data and nucleosynthesis. It must occur before the universe cools enough for nuclei to form, and it must not disrupt the success of Big Bang nucleosynthesis. These constraints force every model to keep pace with the thermal history of the universe, making the Higgs era an unavoidable timestamp. The Higgs field does not tell us which mechanism definitely created matter, but it tells us very clearly which mechanisms are almost impossible within the standard model, because the electroweak phase transition is not strong enough with the measured Higgs mass, and therefore the existence of large amounts of matter forces the file to open in two directions. Either new physics intervened during the Higgs era, or the asymmetry was generated earlier and then processed through sphalerons before electroweak symmetry breaking closed the door. And once attention turns toward the possibility of new physics or an earlier mechanism, one field cannot be ignored. If there was a phase that injected energy into the universe, smoothing and flattening space-time from the outset, then it becomes natural to ask whether the Higgs, already known to be a scalar field, plays any role in the dynamics of inflation, or in the reheating era that followed. Why do cosmologists care about the Higgs, even when studying inflation? And why might inflaton and Higgs be dangerously close cousins? What makes many cosmologists unable to ignore the Higgs when talking about inflation is a very specific paradox. Inflation requires a scalar field to drive extremely rapid expansion of space, while the Higgs is the only scalar field humans have confirmed with colliders. That means if the universe ever used a kind of field engine to pump energy into space very early on, the Higgs is the closest candidate we have ever physically touched. Although observational constraints make that path so narrow, it is almost like walking a tightrope. We begin with what inflation is used to explain in the standard model of cosmology. Inflation is an extremely early phase of accelerated expansion, introduced to resolve problems of flatness and homogeneity of the universe, while also providing a mechanism to generate the primordial perturbations that later grow into large-scale structure. Planck's cosmic microwave background data measured the scalar perturbation spectrum with high precision, finding a spectral index of about 0.965, slightly different from 1, and no clear evidence for tensor modes placing an upper bound on the tensor-to-scalar ratio R at a small value. These are precisely the kinds of signatures that single-field slow-roll inflation models can produce, but not all such models survive these constraints. In the most minimal description, inflation is driven by a scalar field called the inflaton, with a potential that is sufficiently flat over some range of field values, so that the field rolls slowly and potential energy dominates, creating an effective negative pressure that stretches space. No equations are needed to grasp the core point. If the potential is too steep, the field rolls too quickly. Inflation ends too early. and the correct perturbation spectrum is not produced. If the potential is too high in the wrong region, it generates tensor modes larger than the observational limit. If the potential has rough structure, it can produce features in the perturbation spectrum that Planck does not see. Cosmology, therefore, imposes very strict geometric requirements on the inflaton potential. Now place that requirement next to a fact from particle physics. The Higgs field is a scalar field. It has a potential. It has a vacuum expectation value. And crucially, it has excitations that have been observed. The Higgs mass has been measured very precisely at around 125.09 giga-electron-volt from the diphoton and 4 lepton channels in Run-1 data. And knowing this mass allows predictions of couplings and cross sections within the standard model to be compared with measurements. For a cosmologist, this is a hard-to-resist attraction. Inflation needs a scalar field. The Higgs is a real scalar field. If there were a way for the Higgs to play the role of the inflaton, one could connect an early phase of the universe to a component already verified in the laboratory. That idea is precisely what was developed in the Higgs inflation model of Bezrukov and Shaposhnikov, in which the Higgs is non-minimally coupled to space-time curvature, an interaction of the form Higgs field times the Ricci scalar to flatten the effective potential at large field values and produce inflation consistent with observations. This proposal has a very technical appeal. It adds no new inflaton, no new fundamental particles, but instead changes how the Higgs feels gravity when the field reaches very large amplitudes. But as soon as you say this, the problem immediately becomes a discipline test, because you are coupling two very rigid datasets within a single model. On one side is cosmology with Planck, and constraints on R, on N, S, and on the shape of the spectrum. On the other side is collider physics, with increasingly precise measurements of the Higgs mass and couplings which constrain the shape of the potential and the running of interaction constants. The parameter region where both sides are simultaneously satisfied is often narrow. That is why the description tightrope is not rhetorical exaggeration. It is an accurate description of the nature of the problem. There is a deep point here that can be stated very clearly in words. For the Higgs to act as the inflaton, one must consider the Higgs field at amplitudes far larger than its present-day vacuum value of 246 giga-electron-volt. At such amplitudes, quantum effects modify the effective potential. Part 6 already showed that the notion of stability or metastability depends strongly on the running of the Higgs self-coupling and on the top quark. This creates a practical issue for Higgs inflation. If the Higgs potential at high scales becomes unstable or develops unsuitable structure, inflation will not proceed in the required way. As a result, Higgs inflation must be accompanied by a serious analysis of quantum corrections and stability, and it is often sensitive to measured values, such as the top mass, and to choices of the non-minimal coupling. Some studies have shown that Higgs inflation can remain compatible with data under certain conditions, and there are even variants in which the non-minimal coupling parameter can be smaller than in the original versions, depending on how quantum effects and boundary conditions are treated. At the same time, modern reviews emphasize that when performing frame transformations and field redefinitions, the effective potential becomes complicated, and approximations must be handled carefully to ensure stable observational predictions. This is the point where many first encounter the danger of inflaton and Higgs being cousins. If they are too close, meaning they are actually the same field you gain by not needing new particles. But you also accept that every small deviation in high-scale physics feeds back into inflationary predictions, and you lose the freedom to choose the potential arbitrarily, as in independent inflaton models. Another important reason cosmologists care about the Higgs, even if they do not believe in Higgs, inflation in the narrow sense, lies in reheating. Regardless of who the inflaton is, the end of inflation must transfer the energy of the field driving expansion into particles and radiation, so that the universe returns to the standard hot Big Bang trajectory. This process is called reheating, and it may include a non-linear preheating stage, in which energy is transferred very rapidly through parametric resonance. Introductory notes on reheating describe how, when the inflaton oscillates around the minimum of its potential, its energy is transferred to other fields, returning the universe to a particle-filled state. Because the Higgs is a known field, it is a natural target for reheating or for coupling channels between inflation and the standard model. Even if the inflaton is not the Higgs, it must still communicate with standard model fields to produce matter and radiation. The Higgs, because it couples to many particles and sits at the center of mass generation, often appears in reheating scenarios as a portal. This is why cosmology cannot treat the Higgs as a collider-only detail. It is part of the framework linking the early universe to familiar particle physics. There is a technical story behind this that is often skipped in quick accounts, but is worth keeping because it tightens the logic. Inflationary predictions derived from Planck depend not only on the shape of the potential during inflation, but also on the reheating history. Because reheating determines the relation between the observable wavelength scales in the CMB, the time during inflation when those scales crossed the pi horizon. Advanced notes on reheating emphasize that reheating affects the predicted N, S, and R of specific models. In other words, you cannot simply choose a nice potential and stop. You must answer how the inflaton dumped its energy into the standard model, and that path can run through the Higgs. Thus, the tightrope here has two overlapping strands. The first is the cosmology strand, demanding the correct N, S, small r, a nearly power law spectrum, and no clear features exactly as reported by Planck. The second is the particle physics strand, demanding that the Higgs mass and couplings agree with the standard model within experimental uncertainties, and that any extension not spoil those measurements. When you try to embed the Higgs into inflation, you place one foot on each strand, and the region of stable footing becomes narrow. If you want a concrete example of how collider data constrain cosmology, look at how Higgs couplings are being measured with increasing detail. Technical documents from ATLAS and combined ATLAS-CMS summaries emphasize that coupling measurements are direct tests of the standard model and tools for hunting new physics. In the context of Higgs inflation or reheating scenarios strongly linked to the Higgs, Higgs couplings and self-interactions become parameters that cannot be chosen freely. Any modification large enough to change cosmology risks producing deviations visible at colliders. This kind of two-sided constraint is why many appealing models are very difficult to keep alive. At the same time, cosmology also constrains in the opposite direction. Planck data favor concave potentials within the class of single-field models with Einstein gravity, and show no indication that more complicated dynamics than slow roll are required in potential reconstruction. Many otherwise flexible inflation models are excluded or pushed into corners of parameter space. This forces models that attempt to connect to the Higgs to be especially precise in constructing the effective potential and in handling quantum corrections. So why call the inflaton and the Higgs cousins? And why dangerously close? Because at a fundamental level, both are scalar fields with potentials. If an inflaton exists, it is a very close mathematical relative of the Higgs. Once you already have a real scalar field, it is hard to avoid asking whether that field might have played a larger role in the early universe. But that closeness also makes every small deviation in high-scale physics important, because you are using the same field to explain two phenomena at very different scales, colliders, and inflation. This is where cousins can become identity overlap, and that is a strong hypothesis demanding strong tests. Cosmologists care about the Higgs, not because they need an extra elegant story, but because the Higgs is an experimental object that forces any inflation model tied to the standard model to be accountable. It turns inflation from a problem of choosing a potential to fit the data into a problem of choosing a potential that fits the data without breaking collider results. That overlap region is narrow, and it is precisely this narrowness that makes the story worth following, because it says that if there is a real bridge between early universe cosmology and the standard model, that bridge will leave concrete imprints in data, either in the CMB spectrum or in Higgs, couplings and self-interactions, or in how reheating proceeds. And once you see the Higgs standing at the intersection of inflation, reheating, and collider measurements, a final pressure in the chain of logic becomes clear. If the Higgs mass of 125 giga-electron-volt is not just a collider number, but also a constraining parameter for early universe scenarios, then the next question is no longer simply what is 125 giga-electron-volt, but how much that corresponds to in ordinary mass units, and why a number that small can end up determining the entire mass scale of matter in the universe. If the Higgs boson had weighed even modestly, more or less than it does, the universe you are listening from would not merely look different in detail, it would operate under a different scale of physical possibility. The number that appears again and again in collider papers, conference slides, and detector plots is 125 giga-electron-volt. At first glance, it looks like an internal bookkeeping value, meaningful only to particle physicists working at accelerators. Yet this number is not confined to laboratories beneath the French-Swiss border. It quietly governs the strength of the Higgs field, the stability of the vacuum, the timing of symmetry breaking, and ultimately whether matter can exist in slow, persistent forms at all. To understand why, we begin with something deceptively simple. A mass of 125 giga-electron-volt divided by the square of the speed of light corresponds to about 2.2 times 10 to the minus 25 kilograms. In pounds, that is roughly 4.9 times 10 to the minus 25. These are numbers so small that they defy intuition. No scale, no balance, no human sense of weight can register them. And yet this tiny mass sets the reference point for how the Higgs field behaves everywhere in space. The Higgs boson is not the source of mass by itself. It is an excitation, a brief disturbance of a field that already fills the universe. What matters most is not the particle, but what its mass tells us about the shape of the Higgs potential. The measured value of 125 giga-electron-volt fixes how steep that potential is. Near its minimum, how strongly the field resists being displaced, and how it responds to quantum fluctuations. This is why cosmologists care about that number as much as collider physicists do. The Higgs mass encodes information about the background value of the field, the electroweak scale, and the way the vacuum behaves under extreme conditions. It is not a local property. It is a global parameter. Historically, this realization emerged slowly. When the Higgs mechanism was first proposed in the 1960s, the mass of the Higgs boson was unknown and unconstrained. The mechanism explained how particles could acquire mass without breaking gauge symmetry, but it did not predict the Higgs mass itself. For decades, the allowed range stretched across orders of magnitude. Each possible value corresponded to a different universe, with different reaction rates, different stability properties, and different cosmic histories. As experiments narrowed, that range cosmology quietly came into focus. A Higgs mass near 125 giga-electron-volt places the standard model in a special region. It is heavy enough to make electroweak symmetry breaking smooth rather than violent. It is light enough that quantum corrections do not immediately destabilize the theory. And it sits uncomfortably close to the boundary between absolute vacuum stability and long-lived metastability. This boundary matters because it tells us how robust our universe really is. The Higgs mass, together with the top quark mass, determines whether the current vacuum is the deepest possible state or merely a local minimum that could, in principle, decay. The fact that measurements place us near that boundary is not something collider physicists designed. It is something the universe revealed. From a cosmological perspective, this means that 125 giga-electron-volt controls the long-term fate of the vacuum and the early time behavior of fields during inflation and reheating. A heavier Higgs would push the vacuum toward absolute stability, but would alter electroweak dynamics. A lighter Higgs would make the vacuum more precarious and would change the thermal history of the early universe. The measured value threads a narrow path between these extremes. It also determines how strongly the Higgs field couples to itself. This self-interaction governs the curvature of the potential beyond its minimum. In practical terms, it controls how the Higgs field behaved when it was displaced far from equilibrium in the early universe, and how it might respond to high-energy processes that future colliders could probe. That is why future experiments are not focused only on rediscovering the Higgs, but on measuring its self-coupling. This quantity is directly linked to the shape of the Higgs potential. It tells us whether the field behaves exactly as the standard model predicts, or whether subtle deviations hint at additional structure. These deviations would not be cosmetic. They would alter the extrapolation of the Higgs field to the high energies relevant for cosmology. It is here that the everyday unit comparison becomes more than a curiosity. When we translate 125 giga-electron-volt into kilograms, we are not trying to make the Higgs relatable as an object. We are emphasizing a contrast. Something unimaginably light on human scales dictates the mass of electrons, the strength of chemical bonds, and the energy release in nuclear reactions. It determines whether stars burn steadily or violently. It sets the scale at which matter becomes slow enough to assemble into complex structures. This inversion of scale is a recurring theme in modern cosmology. The smallest parameters often control the largest outcomes. The Higgs mass is one of the clearest examples. It does not merely describe a particle, it calibrates the universe. The discovery on July 4, 2012, confirmed that the Higgs boson exists. But it was the measured mass that transformed the discovery into a cosmological statement. With that number, entire classes of early universe scenarios were constrained. Some models of electroweak baryogenesis became unlikely. Some inflationary couplings became tightly limited. Some vacuum stability scenarios moved from hypothetical to calculable. In that sense, 125 giga-electron-volt is not a conclusion. It is a boundary condition. As experiments improve, the focus shifts from mass to structure. How exactly does the Higgs field interact with itself? Does the potential remain smooth at higher energies? Are there small corrections that hint at new physics? Each of these questions connects collider measurements to cosmological inference. Future accelerators, whether linear colliders or next-generation circular machines, are designed with this goal in mind. They are not chasing a missing particle. They are mapping the geometry of a field. The outcome will inform not only particle physics, but our understanding of vacuum stability, early universe dynamics, and the ultimate long giga-electron-voltity of cosmic structure. It is worth pausing on what this means for the broader picture. The Higgs field does not decide whether the universe exists, but it decides how the universe behaves once it does. It sets the pace. It determines whether energy remains free-streaming or settles into bound systems. It allows time to matter. From the earliest fractions of a second to the formation of atoms, from the first stars to the quiet persistence of galaxies, the influence of the Higgs field is constant and unassuming. It does not announce itself. It does not fluctuate dramatically. It simply holds space in a particular state. And that state encoded in the number 125 giga-electron-volt is what makes slow, structured matter possible. As we close this exploration, it is worth remembering that this story is still unfolding. The Higgs field has told us just enough to understand its central role, but not enough to know whether it is alone. The next measurements will not change the past of the universe, but they may reveal whether the rules we see today are complete or part of a larger framework waiting just beyond our current reach. Thank you for staying with this long journey through one of the quiet pillars of modern cosmology. If these ideas have accompanied you into rest, I am grateful for your time and attention. May the night ahead be calm, and may the universe continue its steady work while you sleep. Wishing you a good night's sleep and a peaceful night.